Alright, welcome to our little mini video series again on signal processing. In the past, actually, we talked about multiple different things. We looked at signal classification, we looked at some properties associated with some signals, okay, and today actually we are going to look at basic signals. Okay, basic signals, what you see as an engineer, and try to use that construct to build our discussion in signal processing. All right. So when you're looking at signals in the past, when you're learning material in other classes, can you think of basic signals that you have used? Okay, you might be thinking of triangular waveforms, square waveforms. All right, but out of those signals that you have learned, which ones can be used as a basic type of a signal? Okay, maybe you are familiar with this concept, and you know what they are already. So let's go ahead with our discussion. So we often use or think of sines and cosines as basic signal types. Okay, and partially that's true in one way, and one can argue against that as well. So let's try to understand why and why not. Okay. Now, sines and cosines, they have time varying signals. They have an amplitude. They can have a phase depending on what your reference is. They can also they are periodic signals. Okay, what does it mean by a periodic signal? A periodic signal, as we learned last time, is a signal that occurs at a given interval. It repeats at a given interval. I hope you remember that. All right. So we know sines and cosines can be used as basic types of signals. However, there is another type of a fundamental signal that you're going to learn in signal processing, which is very important, very basic, very important, and you may have seen it in the past, you may have not, but I encourage you to get familiar, get used to this concept, get used to this construct of using these types of signals that I'm going to introduce to you in our signal processing discussion. Okay, we're going to use them, and they're going to be very useful and simplify your analysis. All right, what are they? They are known as complex exponentials. Okay, very unique, very important, introduced by someone called Euler, and we're going to go look at the Euler's relationship as well. However, this is a very important concept. Let's see what that is, what that complex exponential is. Okay, let's for example, let's take a look at a signal xt, where xt is equal to capital C, e is our exponential function, and a times t, where t is our time, because we are looking at continuous time signals. All right, so this is the relationship, this is the function that we are going to look at. Okay, in algebra, in mathematics, you may have learned that this can be either an exponentially growing or exponentially decaying function depending on a. All right, what does that mean? So if a is larger than 0, if a is positive, then you're going to see that xt is going to grow exponentially. All right, it's going to grow exponentially. However, if a is a negative number, if a is less than 0, then your function, your xt function, is going to decay exponentially. All right, so this is these are two common techniques that you're going the two common signals that you're going to see. Now, what if x is imaginary? All right, what if a is imaginary? I'm not sure you have seen this or not. If you have, then it's excellent. You've seen a unique type of a signal, but let's see what that is. All right, so if a is imaginary, then this signal becomes a periodic signal. All right, in the previous two cases, these cases, it's not a periodic signal. However, in the case of an imaginary signal, this is a periodic signal, and it actually has a very unique signature in frequency domain. All right, so depending on whether a is negatively imaginary or positively imaginary without a real component. All right, what that means is, if you take a look at a, if it's a is imaginary, you can have a real. If it's purely imaginary, jy, this term goes to 0. All right, so that means you only have an imaginary component, and that is the complex exponential that we're going to talk about. However, this y term can be positive or negative. All right, it can be positive or negative. In that case, it represents a pure signal, either in the real frequency, in the positive frequency axis, or the negative frequency axis. So this is a very unique concept. We're going to talk about this in detail in the following videos. I just wanted to introduce you to this complex exponential concept as I'm showing here, and this is periodic. All right, and we're going to actually prove that is periodic in a couple of more pages. All right, so along with this introduction of the complex exponential, I want to actually introduce you to Euler's relation. Euler's relation. All right, Euler's relation is another important concept, very useful for ECE 450 and very useful for signal processing as well, and many other classes. All right, so Euler's relation was introduced by Leonhard Euler, a mathematician in a long time, that lived long time ago, and it's a very unique, very beautiful signal that helps us understand a lot of engineering, mathematics, physics, and chemistry related concepts in a simpler way. Okay, you're going to use it in many other classes, and I hope you will get to learn this very well. All right, so what is Euler's relation? Euler came up with this idea for a signal that is e j to the theta, and that actually can be broken down into two terms, cosine theta and sine theta. All right, so cosine theta and sine theta, it has a real part and an imaginary part. All right, it has a real part and imaginary part, and we are going to look at what that is when we are looking at the complex plane. Okay, in the complex plane. But for now, remember that this is our Euler's relation. Okay. So if we substitute theta to be negative theta, guess what? We're going to have a complex exponential where theta is negative, right? We can write this as j times negative theta. Okay, what that means is the complex exponential has a negative frequency, where this is an angle, so not frequency. We're going to talk about the frequency aspect in a little bit, but it has a negative angle. So that means our relationship is actually going to break down into cosine negative theta and j sine negative theta, which can be further simplified into this relation. All right, cosine theta negative j sine theta. Now, using these two relationships, we can actually come up with an expression for cosine theta and sine theta. okay, which what we're trying to prove in this case is that cosine and sine theta, the signals that we said are basic signals in signal processing, can be further broken down into two frequency components. You don't see the frequency components yet because we don't have the time function in here. So for now, just think of it as you can break the cosine theta and the sine theta down into two complex exponentials which has a positive and a negative theta. Alright, so by adding these two signals, I encourage you to try this on your own. By adding these two together, you will see that you have your j sine theta term cancels out and you have 2 cosine theta. Therefore, you have cosine theta to be equal to this expression. Similarly, if you subtract 1 from 2, you're going to get an expression for sine theta, and they are not the same. See, cosine theta and sine theta, they are not the same. You have a negative term and then you have a j term in the denominator for the sine case. Okay, so this is a very important term, expression, relationship that you should remember. Okay, now with this, now since we know our Euler's relation, let's actually go on to look at a signal and then try to prove that a complex exponential is periodic. Remember, I said that it's a periodic signal, but you know, as engineers, we shouldn't take someone's word for it. We need to try to prove and convince ourselves that it is really periodic. All right, so let's actually try to do that. So I'm going to use a shorter term, complex exponential, or CE. Okay, we are looking at the periodicity of the complex exponential. All right. Okay, so we have our signal here. Now, if you look at this signal, this is no longer, we are no longer representing this as a theta, as an angle. What we're showing here is actually a time varying angle. All right, so this angle actually changes with time. Okay, so when you separate theta into that omega naught and t term, then that means you have a frequency and then theta. Those two together gives you your theta. Okay, and this is for a continuous time signal. All right, continuous time signal. So let's assume this is our complex exponential signal, and now the goal is actually to prove that this is a periodic signal. Okay, so as we know, we learned about this. A periodic signal means that it has a certain period. It repeats at a given interval, capital T. All right, now with that in mind, if that discussion, if it is periodic, if that signal, if the complex exponential is periodic, that means ej omega naught t should equal ej omega naught t plus t. All right, so these two need to be equal. All right, so that means when we substitute t equals 0 here, okay, that means ej omega naught 0 is equal to ej omega naught 0 plus t, which means the signal is repeating after that period, capital T. Okay, an easier way to look at it is, if you think of a sine wave, which is a periodic signal, you have the same value after same amount of displacement from that zero crossing, right, which is our period end point. Okay, so if according to that, if this is a period, if t is its period, it should repeat, all right, after that t period of time. Now with exponentials, what we can do is actually we can break the two terms, the sum into two, it's into a product. Okay, ej omega naught t times ej omega naught simple t. Now with this, actually there's some trick, actually a little bit of magic happening. Okay, what is that? So if you look at omega naught is frequency in radians per second, and we can write it as 2 pi f. All right, and then 2 pi f, actually f is 1 over t. F is 1 over t. Therefore, we can say that omega naught t here, omega naught t, t and t cancels out, and we are only left with 2 pi. Right? So what we'll have ultimately in this place is ej 2 pi. Okay. Now ej 2 pi from Euler's relation, what we can do is ej 2 pi, we can write this as cosine 2 pi plus j sine 2 pi. Okay. So what is cosine 2 pi? Cosine 2 pi is equal to cosine 0, which is 1, and sine 2 pi is equal to 0. Therefore, we can say that ej 2 pi is 1, and voila, we have our ej omega naught t. So if you start with this relationship, okay, and actually this should be ej omega naught t plus t. Okay, so that means you started with that signal and you ended up with our original signal. So that means this is true. Therefore, the complex exponential has a period of capital T. Okay, so this is how we prove, this is how we show that the continuous time complex exponential has a period of capital T, and it is a periodic signal. So that means the complex exponential here that we are going to use has a unique frequency omega naught, and only that. Okay, only one frequency component. And in the next video we are going to look at what is this complex exponential, how can we actually truly understand, and using Euler's relation, how can we actually get a feel for, or get a better understanding of what this means in time domain, or what this means for signals. All right, we're going to try to understand in the next video, and then we are also going to look at the frequency content in a sine and a cosine by using complex exponential as a basic frequency component. Okay, so if we have a positive and a negative component, how can we actually show or represent this in the frequency domain? So we're going to go look at that in our next video. Thank you for your attention.